Um, can you hear me correctly and can you see my screen?
Yes.
Okay. Okay, so thank you. First of all, thank you so much to Christoph, Hugo, Alessandra as well, and the people in the University of Rome Tor Vergata to give me the opportunity of giving this talk. It's very exciting to me to have this opportunity. And today we will be looking at classification of orbital motions with deep learning and time series data. You have here information about how to contact me by email, by Twitter, GitHub, which is, I think, the platforms that I use more frequently. First of all, I would like to say that this is work that I am doing in collaboration with some colleagues, as you can see in this slide, which are Alessandra Celletti from the University of Rome Tor Vergata, Katalin Gales from the University of Iași, and Massimiliano Basile from the University of Strathclyde in Glasgow. So all of us, as I will explain later, became together into this project due to our collaboration in a network which is called Stardust Reloaded, which is actually coordinated by Professor Massimiliano Basile. And this is like, this work that I'm presenting now is like a spin-off of that network, we could say. And one important thing to say is that there's going to be a paper that submitted very soon that will expand the general idea and the initial experiments that we'll be talking of in this talk. Okay, so please, if you are interested in the topic, check out hopefully in 1 month we will be able to submit a preprint. Let's see. Okay, so before diving into the content of this talk, I will start talking a bit about me and about what I'm working on right now, aside from this project, but in relation also to things about space. I am a PhD, as Christoph said, in computer science. I got my PhD working in the Autonomous University of Madrid, together with Airbus Defence and Space. And now I am an assistant professor at UPM, Polytechnic University of Madrid. I've made in these last years 2 research stays. One was during my PhD in Glasgow, in the UK, in 2017, in the Department of Mechanical Engineering with Professor Max Basile, and that's where I met him. And the other one was 2 years ago in Krakow, in a group of artificial intelligence there. My research interests are basically now applications of deep learning, deep neural networks, and more specifically, the application of deep learning for time series data, sensors, and so on. And some of the research projects that I work right now focus on the application of AI to space, in which I could remark the project Stardust R, which is I will be talking about it in a minute, and projects also about the application of AI for Industry 4.0 domains. Okay, so I will talk briefly about my work in Stardust R, which is not related directly to celestial mechanics, but to space traffic management. And the project I'm involved on in this network is called Advanced Machine Learning and Computational Techniques for Space Traffic Management. And our goal here is to develop advanced machine learning techniques for collision avoidance and for maneuver recommendation. And so the general idea is to being able to train machines that in a fast way can predict the probability of having a high risk collisions between 2 objects in a space. Also, to be able to plan in advance collision avoidance maneuvers and make all of this in a friendly way, so to speak, so that it's useful for an operator. Currently, we are dealing in this line of research with what is called the all versus all problem, in which we try to analyze the whole catalog of objects in space at once, which is basically a problem in terms of computational time, and that's where AI can play a benefit. So we try to leverage the power of artificial intelligence techniques to create fast filters let's say in a whole and big catalog of objects, fast filters to discard those pairs of objects who do not deserve to be analyzed in terms of collision. So we work with different AI models, such as time series models, tabular models. We are now working with different and new machine learning trends, such as self-supervised learning and graph neural networks. Well, my work here is to supervise the work of an early stage researcher. And I also, in this project, we work in a secondary, so to speak, research line, whose aim is to develop an end-to-end tool for uncertainty quantification from space weather to collision risk using computational intelligence techniques. And our goal here is to use what is called neural-based forecasting, which is the use of neural networks and deep learning for time series forecasting in order to forecast space weather signals like the solar flux, for example, to be, let's say, integrated in all this uncertainty pipeline. And we are, as you can see in these slides, we have managed to do some publications in this regard. Okay, so that being said, this is the outline that I will be following during this talk. First, I will start with the problem statement, the research question that we have, and the motivation of how this work and this collaboration was born. And when we see how this was born, we will see what problems we had and how we decided to move from the data that we had in the very first tries to time series data. So we will talk in section 2 about how we move this problem to time series data. And in that moment, I will go in section 3 to talk about how machine learning is used for time series analysis, more specifically for time series classification, which is the exact task in which this project is framed on. And also, since the techniques that we are using for the time series classification are deep learning techniques, we will go through some basics on deep learning, not all of deep learning, but the parts of deep learning that are most relevant for this work. And then in section 5, we will see how all of this goes together and integrates in the process of classifying time series for the context of this work in section 5 and 6. And finally, since, as I said before, this is part of one paper that we are preparing right now, I will enumerate some of the additional experiments that will be found in the paper so that interested audience can see those experiments in the paper, hopefully very soon. Okay, so we will start with the problem statement and the preliminary work. So in this diagram, we can see in a nutshell what is the main goal of AI in this work. By the way, you see here in this box the name ML Chaos. This is the name that we use, the code, the name of the baby, let's say, of the name of our techniques, let's say, of this approach that we are using for analyzing and classifying regular and chaotic motions. We have called it ML Chaos. So what we have is that we are here in this part of the pipeline, in the upper side of the figure, we start with a motion. And normally, if you want to give a dynamical index such as regular or chaotic to a motion, you do it by the use of a dynamical indicator, such as the fast Lyapunov indicator that we will see later. So, and that gives you which type of motion you have regular, chaotic, and among regular, we have distinguished between rotational and librational. We will see more of this later. So the idea is, the main question is whether we could use AI, machine learning, to replace the use of dynamical indicators in the classification of the type of motions. That is, and hopefully, not only if we can do it, but if we can do it in an accurately way and in a faster way than the way we use with the dynamical indicators, and using just observational data. Just with the raw observations, are we able to compute in a fast way with AI the type of motion? That's let's say, the main research question, pretty simple, under this work. Okay, so how this was all originated? So as I said before, all of the authors that compound this work belong to the network Stardust R, and as part of that network, I think it was May 2020. Yes, May 2020. I was one of the organizers of one training school for that network. It was called the Local Training Workshop 1. That's what you see here, LTW1. And as part of that workshop, I started collaborating with Alessandra Celetti and Katalin to create a problem for the students of that workshop, in which they had to use machine learning techniques to classify the type of motions in a toy model, which was similar to the force pendulum. You have one figure here. And the data that we gave to the students in this workshop was some initial conditions, such as the resonant angle, the motion, and the semi-major axis. And also we gave them the fast Lyapunov indicator computed for different periods of time, 1 year, 2 years, 3 years, 5 years, until 19 years. And actually, this column here of FLI 19 was the one used to assign a label, a dynamical index, to each of the motions. Here, each motion is one row in the table. So we asked the students to train a machine learning model, more specifically a tabular machine learning model, because it learns from table data, from tabular, and to train on different input data, for example, train only on the initial conditions, resonant angle and semi-major axis, to see how the performance improves, including 1 FLI or 2 FLIs or 3 FLIs and so on, and see in any case how the performance varies, which are the most common errors, and so on. And well, if you want to see more about this initial, let's say, this preliminary work, all of this is public. The proposal of the work that we give to the students is in the GitHub of the Local Training Workshop of Stardust R. And you can see it here. And with this approach of tabular machine learning, classic, when I say tabular here, I'm talking about techniques, classic techniques like decision trees, random forest, support vector machines. Classic machine learning was used, well, even classic neural networks as well. This type of algorithms and techniques were used here to create these predictions of the dynamical index. And the accuracy that was obtained by the students in this project was around 80%. The accuracy is for those that are not familiar with this concept of accuracy in machine learning, when we are talking about a classification problem, the accuracy is the percentage of correctly classified predictions by the machine. So we had an 80%, depending on whether we use different FLI indicators to train the model, the machine, or not. We had more or less accuracy, but it was, let's say, the average of the student answer was around here. So after this initial collaboration, we asked ourselves the question, okay, can we do better than this? Can we do better than this 80% of accuracy? We will see that the answer is yes, of course. And one of the keys was to move from this representation of a motion as a row in a table, so to speak, to move to a representation of a motion as a time series. So what we pass to the machine is not only initial conditions, but it's the whole trajectory of the motion of the observations. So this is basically the main movement that we did after this preliminary work. Before going into how this time series motion look like and how we pass it into the machine, I will talk only a bit, because this is not, as you can imagine, my area of expertise, of the dynamical models that we are considering in this work. Some of them, actually, in the paper there are more, as I will say after that. And we consider one-dimensional time-dependent Hamiltonian systems in which there are two variables, y and x, which are the conjugated action angle variables. And we have always this epsilon here, which is the perturbing parameter. Is the higher value this is, the more chaotic motions we have in the system. And we consider three models: the force pendulum with two harmonics, you see here as H2, the modified force pendulum with three harmonics, which we see here as H3, and the modified force pendulum with four harmonics, which you see as H4. Okay, and here in this slide, we can see the Poincare maps for all of these dynamical models that we are considering for the initial experiment of this work, and different values of epsilon. Here is Poincare map for H2 with epsilon equals to 0.02, epsilon equals for 0.03 here, and here it's the Poincare map for epsilon for H3, and this in the lower right for H4. And so this is how, since I said before, a motion was a row in a table before. So now in our new representation, to try the new machine learning, a motion is a time series. A motion is described as a two-variable time series with the trajectory of y and x. So we have yt and xt as the conjugated action angle variables in the action angle coordinate space. We can plot a motion here also as a Poincare map. You see this blue trajectory here, blue line in the map. Normally x, the angle goes from 0 to 360 degrees, and the action, we move it from, I think, from minus 0.5 to positive 0.5, depending on the system that we're considering. This could be how, if we used the default way of plotting a time series. The default way of plotting a time series is just at the time in the x-axis and the value of the variable in the y-axis. This would be how this motion, for example, would be represented. But obviously, for the purpose of analyzing the performance of the network, we are interested in a representation that helps us understand the machine. So we use always this Poincare map representation. Here you can see that there is a point which is yellow. It indicates the initial condition, the initial x0, y0 of the motion. So these time series are obtained by integration the equations of the motion that we saw in one of the previous slides through a fourth-Runge-Kutta method for a time span of t equals 400 pi with a fixed time type step equals to 2 pi over 3. But we consider only the points that we see in these Poincare maps are not all the points of the time series after the integration, but only a subsequence of 200 points. And all the time series that we consider in our data set have the same number of points, which is very important for training neural networks, actually, that all of the data, all of the time series data has the same sequence length. So in our case, all of our motions are for the machine, are sequences of 200 points and 2 variables. So 400 numbers would be. Okay. So this would be if we think about machine learning as input is X and output is Y, and we have to give examples to the machine of X, Y pairs in order to make it possible the learning process. This would be the X, the time series, and the Y, as it was before in our previous preliminary work, is the dynamical index. And we compute it through the use, well, we computed in the paper, we will see different ways of computing this dynamical index. But for this presentation, I will talk about the fast Lyapunov indicator, which was the first one that we used to see if this approach was promising. So the FLI allows us to characterize the dynamics of and distinguish between regular and chaotic motions. So we distinguish 3 types of motions: chaotic, librational, rotational. For each value of the parameter epsilon in the motion, we compute the FLI for a grid of 100 times 100. Well, it's 101. So it's a total of more than 10,000 initial conditions in the XY action plane. And as I said before, X ranges in the interval 0 to 360, and Y range in the interval minus 0.5, 1.5. And depending on the value of the FLI, we classify the motion using different thresholds. So low, we can see it here. Here is the FLI map, so to speak, in the XY plane. And this would be, although here you see it as almost a continuous thing, here in reality we have 101 points times 101 points. This is a map of 10,000 points. And the darker values of the FLI are translated into a label which is regular or rotational, and the highest values of the FLI are translated into a label which is chaotic, which is here the yellow points. And if the values in the middle are considered here like librational. Okay, no, well, actually the ones here, so you can see the translation between the values of the FLI and how these continuous values of the index of the FLI are translated into discrete labels so that we can train the machines on these labels. You can see that there are here some green points spread through the map, and these points correspond to a 4th label apart from rotational, librational, and chaotic, which could be uncertain. In this case, these motions, since we could not give a certain index with the FLI, we decided to leave them aside from the training, and we give the uncertain label. Okay. Oops. So machine learning wise, this could be the problem. We have 3 classes, 3 possible outputs: rotational, librational, and chaotic. These are examples with this is a zoomed version of this thing, but this motion and this one are the same. It's an example of a rotational motion. This is an example of a librational motion. All of these are from the model H2. And this is an example of a chaotic motions. So the idea would be to train the machine with these X and Y pairs, and then test if for new data that the machine does not know the label, we can guess what is the label. This is a typical classification problem. Okay, so we have 3 classes, and as the output and the input is a time series of 2 variables and 200 points. Okay, so once this has been seen, we will see a bit of the backgrounds in machine learning for time series analysis. Okay, I will go fast in this regard because it's just some backgrounds, and I will pause a little bit more in the application of this to the problem that we saw before. So this is a diagram of the different machine learning tasks that we can find for time series analysis. We have, as always in machine learning, the supervised techniques and unsupervised techniques, depending on whether we have labeled data or not. We have labeled data. We have our labels are dynamical indexes. So we're in this family here, and here we have classification or regression, which is our case, of forecasting whether this is the task of predicting future values of the motion in the future. So our task could be this one, classification. Okay, the input is a time series and the output is a discrete label. Okay, so this is a summary. The task of time series classification is a supervised learning problem that aims to predict a discrete label from an unlabeled time series. You see, so I pass here one time series, and it says the machine says 2 3, 2, 1, which is the codes for, let's say in our case, librational, rotational, chaotic. Okay, some of the most popular time series classification techniques in the literature are based on similarity-based techniques, which are basically you take one distance that is proper to measure the similarity between two time series, such as you can even use the Euclidean distance if the time series have the same length, or there are others that are more adapted for time series like the dynamical time warping. And so you create like a one nearest neighbor classifier, which is basically I see which time series in my data set is closest to the time series that I want to classify. And what I do is to say the label of this new time series is the same that the label of the closest one to me. So another family of techniques are the feature-based techniques, in which we transform the problem of time series into a tabular problem by extracting features of the time series. For example, if I have this time series, I say, okay, which is the minimum value of the series, which is the median, which is the mean, and different features, characteristics that convert this time variable into a set of static indicators, into a set of static features, characteristics, and then use that matrix of features to train a classic tabular machine, like a random forest or whatever you want to use from the literature of classic machine learning. And last but not least, what we are focusing on here is deep learning. Okay, so deep learning, what is now I will use this as a way to continue with some basics on deep learning. So I will be using words that you may not be familiar with, like architecture. With architecture, I will refer to the functional form of a model, parameters and weights, which are the things that we want to optimize in a neural network, predictions and results, which are the same thing, the loss function, which is the measure of the performance of the network. And when I say targets or why, I'm referring always to the dependent variable, okay, which is the labels in the context of classification. It's a bit of jargon. So this is a diagram that shows how deep learning, although the keyword is something that may seem new, actually it started to be popular around 2012, 2013. The reason why it became popular is because some researchers managed to train neural networks in a faster and efficient way using graphical units, GPUs. And that was when, let's say, the use of neural networks became available to everyone in a faster and efficient way. But the foundations that we will see now of neural networks are not new at all. They come from actually the 40s or the 50s. So deep learning basically is a way of saying machine learning with the use of neural networks. Okay, this is what we are referring when we say deep learning. And so, what is a neural network? As I said before, neural networks are not something new. Actually, the first model of an artificial neuron is from, I think, the 1943 or so. And they are described as universal functions approximators. So the idea is that we, with this model of the artificial neuron, which have some inputs that in its origin were binary inputs, you have some outputs, and you have one activation here that sums up the values of the inputs and applies one bias to these values. So basically what you have here is that each unit, each neuron in the model is performing a way of linear regression, okay, a linear function. This is what is called the perceptor in the history of neural networks, in which inputs, unlike this other classic model where the inputs were binary, here we have continuous numbers, and we have some weights. This is one very important concept for a neural network, and the weights have to be adjusted so that the prediction of the machine, the output of the machine, becomes closer to the target that we want to achieve. And so at the very end, and this is one of the reasons why this works so well on GPUs, the main operation that is done in a neural network is matrix multiplication. So almost between all the layers we have multiplications. Okay, these are, for example, you have the input layer of a neural network, x1, x2, x3, x4, and you have this output layer. And you consider that each neuron is connected to each neuron. What is being happening under the hood is that only matrix multiplication between the weights of each of these connections to the value of each of these activations of each of these inputs. And you add some biases. As you see, this is just A times X plus B, classic linear algebra formula. Okay, and with this you have the activations of the next layer of the neural network. But not all of the neural network is a linear function, because if it was on everything linear, you could not be able to approximate with a neural network functions that are non-linear. So what you do is, well, this is just the concept of going deeper. What you do to be able to approximate non-linear things with a neural network is to include, after its matrix multiplication, after its instance of a linear function, you include what is called activation function, which is normally a non-linear function like this one. This is actually the most popular, which is called rectified linear unit. And with this inclusion of non-linearities between the layers of a neural network, you achieve this balance between linear and non-linear operations that makes you, in theory, be able to approximate with that paradigm any function. Okay, so I will go to the concept and what is the way that we use in a neural network to measure the performance of the network while we are training. That is the loss function. The loss functions are used to frame the problem to be optimized with deep learning. And these are the most popular loss functions that we use. For regression, we use the mean square error. And for classification, we use the cross entropy loss, okay, which is nothing else but let's consider this is the output of a neural network. Well, and this diagram is very handy because it has 3 outputs, which can be in our work can be considered, let's say, as the outputs for the class rotational, output for the class librational, output for the class chaotic. So what you do to compute the loss function, the cross entropy loss, is to take the softmax of these activations of these logits, they are also called logits, to make them a probability distribution. And once you have this, you compare them with your target vector. Oops, sorry. Your target vector, which is everything zeros, but a 1 in the position where you, which corresponds to the true label of your motion. In this case, let's say that this is rotational, librational, chaotic. So this would be the target that indicates that motion is librational, and you compute the log likelihood between this vector and this one. Okay, and this is the most common loss that is used to tune the weights of the neural network. So you compute this loss function and you compute the derivative of the loss function with respect to all the weights of the network. And you use what is called a process which is called stochastic gradient descent, which is very common in the world of optimization. You use these derivatives of the loss with respect to the weights to update each of the weights in an iterative process. Okay. Okay, and in this slide I want to highlight the reason why deep learning is so popular nowadays is not because the algorithms are super new, because some of the architectures that we are going to use and see in this work come from the 80s, but it's because the availability of powerful hardware and implementations of neural network training in graphical processing units that makes this possible. Okay, in this work, more specifically, we are using one GPU, which is 12 gigabytes of memory. I don't think you need more, because since it's time series data is not like when you work with images that you need a lot of memory to save the images. Each image is a lot of pixels. Here it's just 400 numbers per item, so it's not too much. And with 12 gigabits of data of RAM of memory, we can train these models for this problem. And also here I list some of the deep learning frameworks that are normally used for training neural networks. In our case, we are using these two, fast.ai and PyTorch. These have been the ones used for the implementation of our neural networks in this work. Okay, so more specifically, how we can apply deep learning for time series classification. So normally, the use of time series and neural networks also goes back in the 90s. I think they were used when the use of recurrent neural networks. And only lately, it has been seen that the use of convolutional neural networks, which is an architecture that we will see now, are also very handy for especially for tasks of classifying time series. Okay. So recurrent neural networks are the architecture of the way of creating a neural network, which seems more natural to analyze time series data, because its definition is just a loop. It's like a defining of a neural network with a for loop, in which each input you pass it to a neuron here, which is called the hidden state here, the hidden layer, and its hidden neuron also takes feedback for the last hidden state. So you create here like a sequence of representations that, in a way, the neural network architecture is inheriting the sequential nature of your data, right? But what we are going to see in this work, and what we are going to apply for the problem of classification, is the use of convolutional neural networks, which are super popular in the world of image classification. And how these convolutional neural networks work? So they work with convolutions. A convolution in the world of images work in this way. You take what is called a filter or a kernel, which is a sequence, a grid, in the case of an image, a grid of values like this one, and you applied it, just slide it through your matrix of pixels in the case of an image, summing up all the values, multiplying its value of the grid of the filter, which is the corresponding value of the pixel, and you sum everything up, and you create what is called a feature map. Okay, so the task of the convolutional neural network is to learn the best. These things here would be the weights of the neural network. This would be the things that you try to learn to efficiently create feature maps that classify correctly the image or the time series that you want to classify. Okay, you also have another type of layers in convolutional neural networks, which are known as pooling layers, which take a feature map which has been created by a convolution and summarize the content of the feature map. For example, you can summarize the content of the feature map, taking the maximum of the map, taking the average value of the map, and in that way you create downsampled representations of your map. So this idea of image and image convolutions translated to time series is trivial. You just, when in image we have two-dimensional filters, so here you can think of a time series as a one-dimensional image, right? So when we had previously a two-dimensional filter, now we have a one-dimensional filter that we applied. Let's say this is a sliding filter. This is a sequence of numbers that we apply in the same way that we apply the convolution for image. We apply it in a sliding window fashion to all the variables, to all the channels of our time series. And with that, we create different feature maps, one-dimensional feature maps, and we apply the pooling and all the things that work for images. So basically, if we think of a time series as a one-dimensional image, all the things that work for image can work for time series as well. So once we have the idea of convolution and pooling, it's only, as it always happens in deep learning, a matter of going deep. So this could be one diagram of how a convolutional neural network looks like for a time series classification. Normally, the input time series or array, a tensor is just an array in a GPU, in which in one dimension you have the number of time series that you pass to the network, which is called normally the batch size. In other dimension, you have the number of channels or variables that you have. In our case, it would be 2, one for the X and one for the Y. And you have also the dimension of time, which in our case would be 200, because we have 200 time points per motion. So let's say that we passes to the network batches of 64 time series per iteration. This vector, this tensor here would be 64 times 2 times 200 for our case. So the different convolution operations create different feature maps. Depending on the number of filters that you use, you create different feature maps that contain different representation abstractions of knowledge in your data. And that knowledge is again used as input for another convolutional layer. So with the deeper you go, the more abstractions you create, the better abstractions you create of the knowledge contained in your data. And finally, you try to pull the information of your last and more abstract feature maps and use that summarized information in a sequence of final layers to get your, these are normal layers, dense layers, in which everything is connected to everything, until you have finally your K output classes. In our case, K would be 3. And then this concept of convolutional linear networks is expanded with the use of what is called residual connections, which is a trick which is also inherited from the world of image. And maybe many of you know the architecture ResNet, which became super popular in the world of convolutional neural networks because it allowed to train much deeper neural networks than what was possible back in the day in 2015, when people used CNNs from scratch, when the trick of ResNet of using, apart from the convolution, second parallel path of the neural network, which basically learns the identity function here. This trick helped to train more stably deep neural networks, even with hundreds of layers. So with this ResNet trick, we arrived to inception time, which is the which is the architecture that we'll be using in this work, which is an ensemble of 5 deep ResNet models. Okay, so finally we will see
5 minutes.
Okay, have time. All of this, how this applies to the motion classification. So with all that we've seen, we will detail the first experiment, which is the training of the network. We will train with data from the dynamical model H2 with epsilon equals 0.01, 0.03, and 0.05. So we have a total of 30,000 time series, because for each value of epsilon, we create this map of 10,000 motions. So we have 10,000 motions per value of epsilon. What we do is to split the dataset between 80% of training data and 20% for validation. And we use the FLI to assign the label for each motion to have the Y. And we filter from the dataset the time series with the index -1, uncertain. As architecture, we use inception time, and we don't normalize the input data. We just pass X and Y values as they are. The loss function that we use, the cross entropy loss that we saw before. And with this configuration in the first experiment and this splitting strategy, 80% for training, 20% for validation, and this model, H2, we moved from 80% of accuracy on average in the preliminary work to 97% of accuracy measured on the validation set. Okay, so these were promising results in our initial experiments. And here we can see some of the errors that the network made in the prediction. Here you see on top of each image, you see the prediction of the network, you see the true label, and you see the confidence of the network prediction. For example, you see here that the network said chaotic, but the truth was rotational. You see here the network said rotational, but the truth was librational. And here the network said librational, but the truth was rotational. And what you can see, but human inspection, is that actually this looks like a chaotic motion. So the network was right. And what was wrong was the labeling process. So this made us think that we had to revisit and improve the way that we label the time series with the dynamical indicator. And maybe we should use different dynamical indicators, because these are not errors that come from the network, but from the labeling process. Also here are, in this plot, I show with a technique which is called class activation map, which are the points in the time series which contribute the most to the classification of each of the motions. And for example, we can see here that for librational motions, especially, only one part of the series, let's say one arm, is important for the classification. In a second experiment, we used the already trained model that we trained for H2 with epsilon 0.01, epsilon 0.03, and epsilon 0.05. We used this already trained model with 2 different validation sets. One was a validation set with epsilon 0.023 here, and one epsilon 0.027. Okay, and these ones, so here we trained with 0.01, we trained with 0.03, and we trained with 0.04, and we validate here. And what we found is that the accuracy, these are the map of machine learning predictions. This is the map of, no, this is the true map. This is the map of machine learning predictions. And this is the confusion matrix that shows the error and the accuracy of the predictions. We saw that for the case of epsilon 0.027, the accuracy was higher than for the case of 0.022. And that's why, the reason why this happened is because epsilon equals 0.027 is closer to epsilon equals 0.03, which was one value used to train the machine. So we realized with this experiment that the closer the motions are to those used in the training network, the better results we have. So if we manage to train the network with a dense sampling of the space of possible values of epsilon, hopefully we will manage to have good values of predictions for whatever new motion we pass to the network. Okay, since I'm getting run out of time, I won't go into this uncertainty thing. Yes. And finally, I want to talk a bit, just the last minute, about the additional experiments to be found in the paper, because here we have seen only two experiments, which are training and testing the network for the same value of epsilon, and training and testing for different values of epsilon, but for the same model. So what we are working on right now, we can find in the paper, is the use of different indexing methods based on frequency analysis, because as we saw in some of the slides before, using the FLI can lead to wrong labels, and the network can be confused with those two. So because the network is saying something that is, by a human inspection, you say that is true, but the label by the FLI say that is not true. So there is room to improve the dynamical indicators, and we are doing it with frequency analysis. We are comparing different architectures, not only inception time, which is the convolutional neural network that we're using, but we are also using LSTMs and different versions of the convolutional neural network. Also, we study in the paper how to use these machine learning predictions to complete the cartography of the model, given only a few samples. So for example, if I have here, I train only in a few points of the cartography of the phase space here, could the machine complete the rest of the map for me? Okay, this is one thing that we're studying also in the paper. And also the generalization capabilities of the network. So what happens if I train with motions of H2, but I test the machine with motions of H3, or the other way around? I train with motions from H3 and I validate on H2. How the performance of training in one model extrapolates to validating in another model. That's a very interesting experiment that we're including there as well. Also, where we study the robustness of the use of fewer points per motion. Currently, we are using, what we saw in this presentation was the use of 200 points per motion, but we are studying how the performance of the network is affected by the use of less points. And finally, we move forward from the conservative models of H2, H3, H4 for the pendulum to the spin orbit case to see how the performance of these same techniques applies in the spin orbit case. Yeah, sorry, I'm always rushing at the end. Thank you for your attention, and I hope that you have enjoyed the presentation.
So thank you, Victor, for this very nice presentation, and also for being very well in time. You started at 3:10, so it's perfectly fine. Are there any questions that somebody from the audience wants to pose now? Let me remind you that at 5 o'clock, we will have a discussion session where any longer discussions can also be put there, and the speaker will also be present. So are there any questions? Please turn on your microphone or write it into the chat and I will read it.